Welcome. In this session, I will discuss an example in which we find limit of a piecewise defined function. Let's say a function defined by different expressions at different intervals. To keep it simple, we'll make it polynomial expressions. If it's a rational function expression, you might have to also combine this with techniques for finding limits of rational functions. So this function is defined as 4 minus x if x is less than negative 3, 1 minus 2x is negative 3 is less than x is less than 2, and negative x if x is greater than or equal to 2. If you want to find the limit of a piecewise defined function at a number which is inside one of the intervals, not at one of the endpoints of the intervals, then the function is equal to the appropriate expression at every number close to where we are finding the limit. So we just proceed as usual. So for example, for the function in this problem, to find the limit at 0, we first note that if x is close to 0, whether x is bigger than 0 or less than 0, it's going to fit in this interval, negative 3 to 2. So f of x is 1 minus 2x, which means the limit at 0 is same as the limit of the function 1 minus 2x at 0. And since it's a polynomial, the limit equals the value 1 minus 2 times 0, which is 1. So this is also the limit of the original function f. But what if we are at one of the endpoints of the interval, so that we have different expressions on different sides? In that case, we have to find the limit from each side separately. So for example, to find the limit of this function f at negative 3, I first find the limits from the left and right. The limit from the left, well, we look at values of x close to negative 3 but less than negative 3. If x is less than negative 3, this function is 4 minus x. So the limit from the left of this function f is same as the limit from the left of the function 4 minus x. And since again it's a polynomial, limit equals value, so the limit at negative 3 is 4 minus negative 3, which is 7. What if we take the limit from the right? If x is close to negative 3 but is bigger than negative 3, so you go just to the right of negative 3, that would give me numbers in this interval, negative 3 to 2. And in that case, f of x is 1 minus 2x, and we find its limit as x approaches negative 3 from the right. Again, for a polynomial, limit equals value, so the limit is 1 minus 2 times negative 3, which is 7. Since the limit from both sides are equal, the two-sided limit exists and equals a common value, namely 7. Let's also find the limit at 2, the other number where the expression changes for this function. From the left, so if I take numbers just to the left of 2, so x is less than 2 but not too far from 2. So in that case, x is between negative 3 and 2, so f of x is 1 minus 2x. And the limit of 1 minus 2x as x approaches 2 is 1 minus 2 times 2, which is negative 3. To the right of 2, f of x is negative x. So the limit from the right is same as the limit of negative x from the right, which is again the value, namely negative 2. But now the limits from the left and right are different, which means that the two-sided limit does not exist. Of course, we could have also done this problem by doing the graph first. If we did the graph, basically what we are checking is trying to see if the different pieces come together at negative 3 and if they come together at 2. At negative 3 they do, because one on the left ends at negative 3, 7, so does the piece on the right. But at 2 there is a break, because the piece to the left of 2, the piece from negative 3 to 2, ends at 2, negative 3. but the piece from 2 to infinity ends at 2, -2, which are different points. This illustrates the basic idea behind finding limits of piecewise defined functions. And we'll stop this session here. Goodbye for now.